Welcome back to Physics 246. I want to do an example today showing how to use error propagation techniques in order to find the value and, more importantly, the error in one quantity that depends on other measured quantities that each have their own errors. So here's the statement. A pendulum of length L, and we're given the length and its error, is displaced from the vertical direction by an angle theta, and we're given a value for the angle and its error in degrees. Find the height of the pendulum h measured from its lowest point. So what we really want to do is not just find the value of h, but to find its error as well. So the first step in a problem like this is to figure out what is the equation for the final quantity, h. And in some cases, maybe some of the homework problems on your assignment, that's given to you. But in other cases, perhaps like this one, we have to figure it out by using the relevant physics. So here I'll draw a simple sketch showing a pendulum, simple pendulum on the end of a string like this, displaced from the vertical position, which would be its equilibrium position, by an angle theta. Of course, the pendulum has length L, and so if it swings down, the pendulum bob makes a circular path, so its lowest point would be down here. And we want to find the height h measured from that lowest point. So all we really have to do is use a little bit of geometry here in order to figure out how we can express that height in terms of L and theta, which are the measured quantities. And it's easy enough to see that if the pendulum in its equilibrium position were down here, then that would have the vertical distance there would be the length of the string, and that would of course be the length L. And then just by a little bit of trigonometry, we can see that this distance here, which is the location of the pendulum bob measured from its highest point, measured from the support point up here, that's L cosine theta. And I've left myself without too much room here, so I'll try to squeeze that in here. That distance is L cosine theta. So what we can see then is that h, which is this height, is going to be the total length of the string L minus L cosine theta. So h is L minus L cosine theta, and I will factor out the L in order to make that expression just a little bit more compact. So we've succeeded in the first step, which is to express the desired quantity in terms of the measured quantities. So now what we want to do is use the propagation of error equation in order to find the error in h. It's easy enough to plug in the values for L and theta, and okay, I might as well go ahead and do that here. So if I plug in the L value and then the theta value, this gives 0.043626. I'm just keeping a few extra digits because I don't know exactly how many I'm going to need when I write down this quantity and its error. And so that's the value of h. And now we want to use the propagation of error equation to find the error in h. So using the equation that's given in the Bevington and Robinson textbook, we know that sigma h squared can be written as the sum of several terms, and this is a bit of an approximation. So we'll have the error in L squared times the partial of h with respect to L, quantity squared, right, plus then the error in theta squared multiplied by the partial of this function h with respect to theta squared. And then there would be the covariance term, which would be written sigma L theta squared times the product of the partial of h with respect to L times the partial of h with respect to theta. And there are even further terms, which are the second order terms, the higher order terms, but normally those are going to be very negligible if the errors in L and theta are small compared to those values. So we will not go beyond the first order terms. And in fact, since we assume that measuring the length of the pendulum and measuring the displacement angle theta are independent measurements, then those errors should not be related to each other in any way. So in fact, we are going to neglect the covariance term and then write this just as the sum of the first two terms. So what we're really assuming with measurements that are independent or non-correlated is that this covariance is approximately equal to 0, which it should be in the limit of a very large number of measurements. So let's go ahead now. The next step will be to find these partial derivatives because we have to substitute into the equation. So that's why it was important to find the equation for h. So the partial of h with respect to L, that's pretty easy because the L only appears here once. And so that dh dl will just be 1 minus cosine theta. And we will be able to substitute in the value for that. And then, of course, it has to be squared. The partial then of h with respect to theta is just slightly more complicated. What we have there, it actually can be useful to go back and look at the original expression for h because L, if we take the partial of h with respect to theta, we're doing it holding L constant. So the first term doesn't give us anything. The second term will give us minus L, but then the derivative of cosine theta is negative sine theta. So the two negative signs will cancel, and we will get L times the sine of theta. And that's the partial of h with respect to theta. So those two then can be plugged in. I will go ahead and rewrite the equation for sigma h, and I'll go ahead and take the square root of it so that it'll be in more or less its final form. So sigma h then, and we realize this is an approximation, but it should be a good one. We'll have this square root term. You know what? That's not very good. I'm going to go ahead and try that again and see if I can do a little bit better job of drawing a horizontal line. That's good. So then the first term, of course, is sigma L squared. And now I'll go ahead and plug in the partial of h with respect to L. So it's 1 minus cos theta quantity squared plus the partial, or plus the error in theta squared times the quantity L sine theta squared. And I have just enough room for that under the square root. All those terms are under the square root. Now I can just go ahead and plug in the numerical values with one important point. The theta that's given to me is in degrees, but when I express the error here, sigma theta, it must be in radians. So here I'm just going to draw a little arrow and remind myself that sigma theta has to be written down in radians in order for me to get the correct expression. Of course, cos theta and sine theta doesn't matter. You can, as long as your calculator is set in the right mode, you can just plug in 24.1 degrees and find the cosine of that. But here, where we have to plug in the error in theta, we'll have to convert 0.20 degrees into radians. All right, and I won't do that conversion for you, but I just mentioned that. So when we go ahead and substitute in the numerical values for L and theta and for their errors, the answer that I get is 0.000, and then it's 725. And it's exactly 725. There's no more digits after that. Of course, that will be in meters. And when we round off the error so that we can express h and its error, we always want to round off the error to two significant digits. So the question is, do I make this 7.3 or do I leave it as 7.2? And there's a rule for that that was described in chapter 1 of the textbook. Whenever you have an error or anything where the final digit is exactly a 5, then you increment the previous digit, you round up only if it's an odd digit. So here, we would not round up to 00073. We would leave it as 00072. All right, so I'll just go ahead and put that in there, 0.00072 meters, because the 2 is even. And the general rule for those rounding cases is that you only round up the digit when the final digit is 5. The digit before that only gets rounded up if it's odd. All right, so there's our error. We write down the final result for h, which is the objective of this problem, rounded off to the correct number of digits. So we have to have the h value expressed so that there are 5 digits after the decimal place. So that will be 0.00, oops, nope, made a mistake there. Let me go ahead and fix that. So it's 0.04, like I had written down up above, 0.0436, and now I need 1, 2, 3, 4, one more digit, 363, okay, plus or minus the error, 0.00072. We'll put the unit at the end, and just to make sure, what we should have in each term, in the value and its error, is that they should contain the same number of digits after the decimal place. They should end in the same place. So here, sure enough, the 3 and the 2 are in the same decimal place. So that's our error, or sorry, that's our result, finally, for h and its error. And there's one more thing we can do to check this, all right? Just to check to see if it makes sense, we can express each of the quantities in terms of its fractional error. So if I just write down sigma h over h, right, and just take the ratio of those two, I get 0.0167, just taking the fraction of those. And then I can compare that to sigma L over L. That's easy enough to do because I'm given the values for L and its error. When I do that for sigma L over L, I get 0.0030. And when I do the same thing for theta, sigma theta over theta, I get 0.0083. And the reason for doing this check is the fractional error in the final quantity should always be more than the fractional errors in any of the individual quantities. And it shouldn't be too much more. It should be a little bit more because the error in L and the error in theta combine to give us the final error in H. So you can see that the error in theta, 0.008, is about half of the error, the fractional error in H, and then the error in L, 0.0003 or 0.003. It makes sense, right? So the relative sizes of those make sense. All right, so I hope this has been a helpful little introduction to how to use the techniques of error propagation in order to solve a problem like this where we're given two measured quantities, each of which has its own error. Here is the error in L, here's the error in theta, and we want to find a result that's based on those two, and we not only want to find the numerical value, but we want to find the error in that value. So take a look at this. If you have any questions, you can come and see me, but I hope it's been a useful illustration that will help you on your homework. And I'll see you in class.